Hey guys, welcome to video 5.3. Today we're going to be talking about gravitation. I'm not sure what this is popping up. Okay, so today we're going to be talking about gravitation, and our title of our lesson is The Apple, the Moon, and the Inverse Square Law. So if you know anything about gravity and Sir Isaac Newton, you may kind of understand where I'm coming from when I'm referring to the apple. But if you don't know about that, I'll save that fun little piece of information for later. Really what we're going to be looking at the beginning of this video is really just a history lesson on kind of how the idea of gravity was proven. So before this time, gravity was understood to exist, but there really wasn't a proof as to how gravity affects planets moving around the Earth and moving around the sun. So, our moon moving around the Earth and planets moving around the sun. So we're going to start kind of our history lesson with this guy called Johannes Kepler. And he was a mathematician, astronomer, and he developed these three laws of the motion of planets. You don't really need to know them or read them, because we're going to talk about them in our next video more in depth. But he came up with these laws of how planets move around the sun. One of them was he was able to figure out that the movement of the planets was elliptical in shape. So this is circular motion, and then elliptical kind of looks like an oval. Okay, so he realized that planets move in this elliptical shape. The sun being the center, being what they move around. That's what's called the law of ellipses. The second one was that you could draw an imaginary line from the center of the sun to the center of the planet, and that they'll cover equal amounts of distance in equal amounts of time. And we'll kind of talk about that one later, so if that one doesn't make sense to you, that's okay. And the last one is that it's a ratio of distance and time. And so the law of harmonies we're going to talk about later. But basically, Kepler was studying the movement of planets, right? However, he did not have an explanation for why the planets orbited the sun. He only knew facts about their path. Well, then Isaac Newton came along, and he was very unsatisfied with Kepler's work. Particularly, he wanted an explanation for why the planets moved. So Newton did come up with his three laws of relating to physics and movement, and one of them was that an object, if it's in motion, that object will stay in motion, right? It's going to continue moving at the same speed in the same direction unless what? Unless it's acted on by an outside force. So I should have written outside. So if we have the sun right here, and here's the Earth, and we know the Earth moves like this, right? It moves in this elliptical pattern. Well, what Newton was saying is, okay, here's the Earth, and you know from circular motion that we could draw a free body diagram like this. Well, I drew that line too soon. I shouldn't have drawn that. The velocity is tangent to the circle. So the velocity is going in this direction. The inertial path would be it continuing in that same direction and that same speed forever, right? The Earth would just continue moving this way forever, and we would all die. However, it doesn't. So since it doesn't follow its inertial path, that must mean there's a force. So Newton said there's a force that's making all of these planets go in these elliptical patterns, okay, moving in circles. The only reason he knew that is because they didn't continue on straight for infinity. They are turning. Since the object is changing direction, we know there must be a force pulling that. And it's not changing direction randomly, it's changing direction consistently. It's consistently changing its direction to form this shape around the sun, which means there must be a force constantly being pulled inward. So if the Earth is here, velocity is going to go straight, but something's pulling it inward. So there's always going to be a force pulling inward towards the sun. So Newton said the reason why these planets are moving in this way is due to a force pulling on the planet, and that force is exerted by the sun. Okay. One quick side note, I would keep talking about the force of the planet, right? It's being pulled in by the sun. Remember that the planet itself is also pulling on the sun. Remember when we talked about Newton's law where every force has an equal and opposite force? So if the sun is pulling on the planet right here, it also means the planet is pulling on the sun with equal forces. The only difference is the planet is so much smaller than the sun that it has pretty much no effect. This pull on the sun has almost no effect on the sun. That's why the sun doesn't move and why this guy does move, because he's much smaller. So the smaller mass means that the force is going to have a greater effect. So Newton kind of came up with this concept of gravity, and Newton never wrote about this, but it's kind of like an old tale that Newton discovered gravity or realized the effects of gravity when he was sitting in his orchard one day when he was 25 years old. Although they always draw him very old with gray hair, but he was only 25 when this happened, or supposedly happened. An apple fell on his head from a tree, and he thought, it fell, that apple moved. It was standing still, and it moved, which means an outside force must have pulled on it, which means there must be a force pulling on us towards the earth. So here's what Newton tried. He came up with this called this Newton's mountain theory. Okay, so this big black circle is the earth. Okay, and that this is Newton's mountain right here. I don't know if you can see it. I'll draw in a different color. That's his mountain. Okay, so he's saying, let's pretend I have this huge mountain. Okay, and the top of the mountain there's no air resistance. So really, let's say that the top of the mountain goes out basically into the edge of space. Okay, so here's space. And he's saying, this is, by the way, a thought experiment. This is not a real experiment he did. In fact, back in his day, it was more common to think through things than to actually experiment with things. Interesting point. But anyway, let's say he has this space mountain right here, and at the very top he has a cannonball and a cannon, and he shoots the cannon. So he says, this is scenario A. If this is your cannon, okay, here's my little cannon, and I'm not very good at drawing cannons, am I? Is that what a cannon looks like? That's not what a cannon looks like. Cannon looks like this. That's what a cannon looks like. Okay, and here's the fuse. Woo! Okay, so here's the cannon on top of the mountain, right? And he says if he shoots the cannonball with a relatively low horizontal speed, it's going to fall back on the earth, right? Which we know that from projectiles. Now he says, okay, well, what if I shoot it with an even greater velocity? Okay, so situation B, here's his cannonball. What if he shoots it with a greater velocity? It just means it's going to go straighter, it's going to go longer before it starts to fall. But eventually, it will fall. The reason I'm drawing it curved here is because the earth is curved, right? The earth is not flat. The earth is curved. So here's my earth, okay? Here's our continents and stuff. So if you shoot it with a greater velocity, it's going to fall, and it's actually going to go a farther distance before it lands, right? So he says, taking this thought, here's his last one, C. He says, okay, well, what if I shoot it with a really, really, really high speed? Then it takes a long time to fall. And then as it's falling, guess what ends up happening? Okay, here's our world. It falls, and it keeps falling, and it keeps falling, and it keeps falling, and it's in orbit. So that's what he was talking about. He said, okay, eventually, if you shoot an object with a great enough speed, at the very tippy top of the Earth, you can put it into orbit. Okay? It's continually having this force pulled on it from the Earth. But since the Earth is curved, it feels like it's falling forever. Let me show you a simulation. So if my drawings were not super great, I'm going to show you my animation here. This animation shows what would happen if there's no gravity, right? Here's your cannon at the top of the mountain. It'll shoot and go on forever, right? Well, when there is gravity, it's going to look like this object right here. And it falls, but as it's falling, the Earth is also curved. So it falls and eventually crashes to the Earth, okay? If I shoot it at a speed that's greater than the one that I just did, then it's going to go farther before it crashes into the Earth. However, once I shoot it at a fast enough speed, it ends up basically falling forever. It's continually falling. And actually, we have calculated if you launch something equal to 8,000 meters per second, it will orbit the Earth. It'll move so fast that it's covering enough distance of the Earth that as it falls, curving, it actually meets the same curvature of the Earth. Now, if you launch something greater than that speed, that's when you get this elliptical pattern, okay? It goes all the way out, but the Earth does pull it back inward, and it looks like it might fall down, but not quite, and so it keeps going back out. So this is the movement of planets. So he was able to prove the elliptical movement of planets based on gravity. So he said, really, these objects that are going around the sun are a lot like projectiles, right? They're moving and continually falling towards the sun, but they're so far away and they're moving at such high speeds that they never actually hit the sun. So I'm going to go ahead and erase this so we can look at the rest of my information. Okay, so Newton had a dilemma. He wanted to prove this mathematically. He wanted to prove gravity mathematically. Already, it was known that objects on the Earth accelerate at this value, negative 9.8 meters per second squared. Okay, this is objects that are on the Earth accelerate to the Earth with this speed. The moon, it was known, accelerates at this speed towards the Earth. So here's the Earth, okay? Something on the Earth accelerates, there's a huge force pulling that object towards the Earth. The moon, which is much further away, has a much weaker pull. Gravity's pull is much weaker on the moon than it is on an object on the Earth. So basically, Newton knew that distance had something to do with the force of gravity. An object that is closer to the Earth has a much greater force of gravity than an object far away from the Earth, like the moon. So he wanted to prove that mathematically. He took the force of gravity on the moon compared to the force of gravity of an apple. That's something on the Earth. And he came up with this ratio, 1, basically 3,060th. Okay, so the gravity on the moon, or the acceleration of the moon, is 1 3,600th the acceleration of an apple. And we know, based on this drawing that we looked at, that that's probably due to distance. And so that's what he did. He did some basic calculations. He said, here's the acceleration on an apple falling from a tree, and here's the radius of the apple to the Earth. So even though the apple may only be 2 meters away from the surface of the Earth, we're always measuring the Earth by the core, okay? The core of the Earth is, I think, 6.8 times 10 to the 6 meters. I'm not entirely sure, but that might be the radius. I'm not entirely sure. And he knows that the radius of the moon is 60 times the radius of the apple. Not the only thing affecting gravity. Distance isn't the only thing. Mass is also important. It also affects gravity. So this is the universal gravitational equation, which I'm going to have on the board. G represents a universal gravitational constant. It represents 6.67 times 10 to the negative 11th, and then these are the units for G, but you don't have to know the units for G. You don't have to worry about that. But this will also be on the board. This is a constant. G is always going to equal this amount, okay? This capital G is not the same thing as lowercase g, okay? This is just a constant. Basically, the force of gravity in between two objects will equal G times the mass of the first object times the mass of the second object divided by the distance between the objects squared. So if we look at this formula, force of gravity equals G times m1 times m2 divided by g squared. What happens when we're changing mass? What happens to the force of gravity when we change mass? This is really important. If your mass doubles on one object, your force is going to double. Okay? If your mass doubles on both objects, so we go from, or I'm sorry, it's not doubling on this one. If your mass doubles on, well, okay, let's look at this one. This is our original equation, okay? Here our mass doubles, and here our mass doubles. What happens to our force? It quadruples, right? It gets bigger. Okay, here our mass is the same, and this mass triples, so our force triples, okay? So mass is going to, increasing mass will increase force. Increasing mass will increase force, okay? Now let's look at distance, the effect of distance on gravity. Okay, so here's your distance. This is our original problem. In this one, we double our distance. Double the distance. What happens to force? It's going to be cut by a fourth. Okay, it's going to be a fourth of what it used to be. If we half our distance, okay, if we shrink our distance by half, the force will quadruple. So force and distance are affected by a quarter, okay? Let's look here. Here, your force doubles, which means this is going to go down by a factor of 1/4, but the mass doubled here, which means force is going to double by 2, but the mass also doubled here, which means it's also going to double by 2. So 2 times a quarter times 2, which means it's going to be the same force. So the force is basically 1/4 distance, and the mass is going to be, or the force is equal to your mass. So if you have, 4, if you multiply your mass by 4, you have to multiply your force by 4 also. Okay, so here's just a sample practice problem. Remember our formula. The force of gravity is the constant G times the mass of one times the mass of your second object divided by your distance squared. So let's say this is the mass of your Earth. That's object 1. Here's the mass of your second object. It's a physics student. Okay, it's object 2. And then this is the distance down here. All you do is plug in your numbers. So here's the mass of the Earth, mass of the physics student, distance between them, and then this is G. Don't worry about the units there, but this is G. And we can come up with the force of gravity on the person pulling is going to be 686 newtons. And if we were to draw a free body diagram, here's the person, here's the Earth. You would show the diagram like this. The person right here is pulling on the Earth with 686 newtons. No, sorry. The Earth is pulling on the person with 686 newtons. But I also want you to show the opposite. If the Earth is pulling on the person is also pulling on the Earth with the exact same amount, right? We should have that memorized. Every force is an equal opposite force. Okay, just to end our video, here's an interesting question. Is there a gravitational force attracting you between two physics students? Well, our formula says that there's always a gravitational force between two objects, always. It's the mass of the first object times the mass of the second object times our gravitational constant divided by the distance squared between them. So if one of you guys weighs 70 grams and one of y'all weighs 85 kilograms, we can figure out exactly what gravitational force is between you two, which means you, without touching them, will be exerting a force on them, pulling them. And they are also exerting that same exact force pulling on you. Interesting thoughts, people. Interesting thoughts. That's it for today.